one of our main goals with rational tangles and their algebraic structure is figuring out how it's possible that only being able to do a positive twist and a 90-degree rotation, how is that enough for us to be able to untangle any tangle? Or is that enough for us to be able to untangle any tangle? And so the first question that we need to wrestle with is, if we take each one of those two movements, each one of those two generators for our rational tangle group, how is each one of those undone? And let's start in this example with the rotation. So if I start with an empty tangle, and I have an empty tangle on my desk here in front of me, so we'll just start with that one. If you have one at home, you can follow along and play the home game, as it were. So I start with an empty tangle. This thing is kind of looping on itself, so pay no attention to that. It's isotopic to an empty tangle. There we go. And so the question is, how many rotations would I need to perform in order to get the empty tangle back again? If I do one, I have now a different tangle than I had before. There's no way to perform an isotopy on this to make it back into my horizontally untangled tangle. So what happens if I do one more? Well, now I'm back to the empty tangle again, aren't I? So it would seem that if I start at an empty tangle, it takes me 2 rotations to get my empty tangle back again. We could also say that as the inverse of a rotation would appear to be just another rotation. But we might also be a little skeptical. Or maybe we should be a little skeptical, because each of these rotations is only a 90-degree rotation. And in principle, 2 90-degree rotations doesn't always give me the same thing back that I started with. Right? It gives me a 180-degree rotation of the thing that I started with. And so it's worth asking, what happens if I start with an interesting tangle, like t cubed? Is it still true that 2 consecutive rotations gives me back that t cubed again? So for the tangle t cubed with 3 twists, all done in a positive orientation, we might expect that 2 rotations is not going to invert, not going to come back to the original. 1 rotation is certainly different than my original. When I do 2 rotations, I find out that actually I still have these 3 horizontal positive crossings here sitting in the middle of my tangle, and 2 rotations has actually given me back my original tangle again. So starting from t cubed, 1 rotation is undone by yet another of the same rotation. And this is my original t cubed again. So maybe it was just that t cubed was too simple of a tangle to find the lie here. Maybe if we have a more complicated tangle like t squared rt, things will be different. So here's the tangle t squared rt. Right? I did 2 twists and then a rotation, and then I did 1 more twist. So that accounts for the 2 sort of vertical twists that we see here, and then the 1 horizontal twist. That was the last thing that I did. So if I do 1 rotation on this, I clearly have something different. If I do a second rotation on this, now I think we're justified in being a little skeptical about whether or not this is in fact the same tangle as we had before. How could we be sure? So remember, the key to understanding when not-like objects are actually the same, the differences that we don't want to care about, are the isotopies, the ways of moving these strands around in space without, unattaching them from the endpoints and without the strands crossing into one another. Anything that I can do to just kind of bend these strands around in space is valid. It's going to give me the same rational tangle, even if maybe something about this diagram that we could sketch a bit might look different. So let's imagine that I can just sort of come in here, and maybe I don't like the fact that this twist over here is on the left side of my tangle. Maybe I want to kind of just tip it over like this. Okay, so this is now the same tangle that we just had a minute ago. Maybe now what I'm interested in doing is, let's see, so that tangle we can just kind of undo there. But then if I can do that, surely I can do this also. And oh look, if I can get it to actually stay. I need to be like, what are the scientists that study butterflies? They pin them down to the table. All right, there's what I need to do. And hopefully, if you take my word for it, I can wrangle these strings into place. We can see that we do indeed have our same rational tangle back. right? We had the one positive crossing happening over here, and then we had these two these two vertical crossings happening next to it. So even when we started with t squared RT, doing two rotations gave us t squared RT back again. Although it wasn't immediately obvious, we had to do some sort of shuffling around of the strands that are in there. In fact, one of my favorite words in all of knot theory is the word that describes the movement that I just did here. It's called a flype, F-L-Y-P-E. That's what happens when you take the whole tangle and we just kind of trying to turn it upside down without moving any of its endpoints. And what a flype tends to do is it tends to take some twists, which are over here on the left side, and it moves those twists over to the right side instead. But it's still an isotopy. All we're doing is we're just sort of moving all the strands smoothly together through space. And so the actual type of rational tangle is not changing, but now we can more clearly see that it only took us two rotations to get back to the original tangle once again. So one of the things that does for us is it illuminates part of the algebraic structure of rational tangles. In particular, what it tells me is that the rotation operation satisfies r squared equals the identity. Every rotation of rational tangles is its own inverse. And that's the first glimmer of the algebraic structure. It tells us how to undo a rotation. To undo a rotation, just do one more rotation and trust in the mathematics that that second rotation has undone the one that was just done. All right, so here's a somewhat interesting, kind of complicated rational tangle. 3 twists followed by a rotation, followed by 2 more twists, followed by a rotation, followed by 3 more twists. And so what I want to do now is just sort of, I want to black box this. I want to capture this tangle inside of an envelope, just sort of freeze all those crossings in place, and kind of begin to ask the question, how would I untangle this tangle? Using the same twist and rotation operations that define the rational tangle group in the first place. All right, so I've packaged up my tangle inside of this envelope. So we know how to undo a rotation in the rational tangle group, right? Even though it might not look like it at first glance. If I were to rotate this thing, I could undo that rotation and give me my same original tangle back just by rotating one more time. But of course, you shouldn't believe me, because we would have to maybe do a lot of, things to kind of, move these strands around in space. But we would eventually be able to undo it. So the question that remains is, how would we undo a twist? Let's suppose that I added one more twist to this outside of the envelope. So I'm going to kind of pull this envelope off to the side, and I'm going to add a twist. So I've added one more twist outside of this envelope. And so the goal now is to cancel this twist. And that's what I want us to kind of do. We're going to do it together as 2 teams and an instructor. So the goal is going to be to somehow cancel out the twist that I just added. So the first question I want to ask you is, what should I do next? If my goal is to cancel out the twist that I just did, would it be smarter, do you think, to do another twist next? Or would it be a better idea to do a rotation next? What do you think? So adding more positive twists, because positive twists are the only kinds of twists we have now, right, in our rational tangle group. Positive twists just accumulate on one another. They just pile up, right? So if after doing one twist, I do another twist, that's not going to get me any closer to being untangled, which is ultimately the goal here. So every time I twist, if I want to get closer to undoing that twist, probably the next thing I should do is a rotation. So what we're trying to do here is fill in the blank. G followed by T, so G is my tangle in my Ziploc bag here, followed by a twist, followed by what is going to cancel out that T. And so our hypothesis now is that the first thing we would do here is a rotation. Okay, second question. Every time I do a rotation, what should I do after a rotation? Should my next step after a rotation be a twist, or should it be another rotation? If I do another rotation, what happens? What do we know about rotations at this point? If I ever do 2 rotations in a row, it's the same as never having done a rotation at all, because every rotation undoes itself if I do it twice in succession, right? It's just like the transpositions of adjacent strings in a permutation, right? It undoes itself if we do it twice in a row. So if my goal is to cancel out this T and get G by itself, my original tangle in the Ziploc bag, right? Then starting with R and then following it with another R is just going to get me back to GT. It's getting me back to my original problem. It's not getting me closer to having canceled out that T. So this kind of tells me that doing another rotation after I've just done a rotation is not very helpful in the cancellation regime. Instead, after every rotation, I should probably do another twist. So I'll do another twist here. I have to put this down to use 4 or 5 more hands. I just added another twist here. And now things are looking even more hopeless than they were before, right? So the tangle we're looking at now is G, Ziploc bag, T, R, T. But if I just did a twist, what should be the next thing that I try? Twist or a rotation?
Rotation.
Rotation. Because I don't want to do 2 twists in a row. Those are just going to pile up on themselves. So this now is GT, RT, R. Right? Okay, this still looks kind of messy. I don't have my original tangle back yet, but I just did a rotation, so what should I do next? I think a twist, right? So we'll just add one more twist. Why not? I just added one more twist. And now the question is, what do we have? Well, we're still not quite there. Notice that my Ziploc bag is kind of oriented vertically, so I probably am not back to my original tangle. So we'll do one more rotation. Now my Ziploc bag is back in its original position. And actually, if I kind of smooth it out here, it turns out I've completely canceled out that twist that I added over here on the right-hand side. So what I'd like for you to do in your group is just to fill out this last parts C and D of activity 2.2.3. which is to fill out the answer to this question, G followed by T followed by what sequence of steps gave me my original G back, having canceled out that one twist, and what, according to your answer, is the inverse of the twist T. Our strategy for untwisting that twist T was to alternate rotations and twists until we've somehow gotten back to our original. And we think that that happens after we've done a total of 3 more rotations in this sequence. So we would say that the inverse of T is RT, RT, R. Or another way to say that is just to kind of take this whole string after here and say that this whole string must be equal to the identity. TR, TR, TR must equal the identity, the empty tangle, right? Nothing happens. That's 2 different ways of kind of saying the same thing. And just to verify that one more time, I've got my camera set up on a little tripod on my desk now, so I can have both my hands to do this. Here was my original sort of messy tangle inside of a Ziploc bag. I did one twist to add a crossing, and then a rotation, and then another twist, top right over bottom right. Strings get kind of short when I do this, but now we've added this additional crossing over there, and then another rotation. That was my second rotation. And then again, I take the top right over the bottom right. Uh-oh. I think one of mine came untangled here. I don't think I went too far, though. Then I do my third rotation. Oh, it came untangled. Well, you'll have to rewind the video when you watch this and see that it worked right the first time. So yeah, that was the inverse for our T. So what we kind of take away from this, one of the things we can take away from this is that in order to undo a single twist, it takes us 5 steps to undo just the one step of adding that twist. So undoing a twist is possible, but somehow it's a lot harder to do than just adding a twist in the first place, right? But now that we know how to undo a twist and also undo a rotation, this should give us a recipe for how to find the inverse for any rational tangle. I'm just going to sort of write these over here. So the inverse of a rotation is the rotation itself, because if we do 2 rotations, we get them cancel one another out. And the inverse of a twist is RTR. And so if I wanted to find an inverse for my tangle that's inside of this Ziploc bag, and the tangle inside my Ziploc bag was T to the 3rd power, R, T to the 2nd power, R, t to the third power. So if I wanted to find an inverse of that, what could I do? I could do the same thing that we did with braids. We could shoes socks it. So if I wanted to cancel out the first letter on this, the first letter I would want to try to cancel out is the last letter in the word, right? The last thing that was done, which was this third twist on the end of my line. So the first thing that I should do, I'm going to write down my Tangle t here, t cubed r t squared r t cubed. I'm going to write that t cubed as t. And then I'm going to try to cancel out this t using an inverse of t. But an inverse of t is RT. So this RT, I would add in there, is going to cancel with that t. Underline those. Now we can imagine that those get crossed out and go away. The next thing I would need to cancel out, according to shoes and socks, is this t, which is at the end of my word. And I can cancel it out by using another RT. One of the things you might notice here is that as I'm writing out the letters for this inverse, I end up writing two r's next to each other. So what can I do to simplify that? What is r composed with itself? Well, that's just the identity, isn't it? So we could just erase those. So we're getting a slightly simpler expression for this inverse. But now we've handled this t, so we move on to the next t. And we cancel it out using the same strategy. Another RT. And once again, I have a pair of r's here that I can just kind of cancel out. And then we can work our way backwards. The next thing I would need to cancel out is this r. How do we cancel out a single r? Well, the inverse of a single r is just another single r. So we'll use another single r to cancel that one out. And so on and so on. So if I keep going here, I'm just going to do all the rest of these steps at once. I need to cancel two more twists with two more RTRs. That would take care of these. Then I would need to cancel that next r with another r. Then I would need to cancel three more twists with three more RTRs. Ugh. And we'd be able to do a little bit of simplifying here because, again, I have a pair of r's next to one another that I can forget about. I have another pair of r's that are next to one another, another pair of r's next to one another, and another pair of r's next to one another, and another pair of r's. So we can simplify a little bit, but still, the expression that we would get for the inverse of this rational tangle is gigantic, right? It's all of this would be a language spelling out the inverse of this rational tangle. And so that works. I mean, there's nothing wrong with that as a way of expressing an inverse for a rational tangle, but rational tangles wouldn't be as magical as they are if there weren't another way to do it also. And that's what we're going to look at to end today.